Imagine a brilliant savant. They've devoured every book in the library, they understand quantum physics, and they can write poetry in multiple languages.
Right, a total genius.
Exactly. But the absolute second they finish their final exam, a switch flips. They just lose the ability to form any new long-term memories.
Oh, wow.
Yeah, you can show them a new tool or, tell them a new fact and they'll understand it perfectly in that exact moment, but walk out of the room and come back. They've completely forgotten.
And that is, sadly, the daily reality of every deployed foundation model today. We spend millions of dollars training these massive parameter spaces, and then we just freeze them.
The intelligence is staggering, but it's fundamentally static.
Right. And the moment you try to teach that frozen model something new, you really risk breaking everything it already knows.
Well, welcome to the deep dive. Today we're taking you through a stack of brand new research from MIT and the Improbable AI Lab.
Yeah, we're figuring out how to cure that amnesiac savant.
Exactly, using a framework called Self-Distillation Fine-Tuning, or SDFT. If you're deploying language models in production, you have almost certainly hit the wall with post-training adaptation.
Oh, absolutely. You want your model to learn a new API or adapt to new medical guidelines without destroying its foundational reasoning skills.
And this paper tackles that exact bottleneck. It introduces a computationally viable method for continual learning.
It addresses a tension that has plagued ML practitioners for years, honestly. Right now, if you want a model to learn from expert demonstrations, the standard paradigm is supervised fine-tuning, or SFT.
Right, which is everywhere.
Yeah, SFT is incredibly popular because it's simple and it scales, but it has a fatal flaw. It's inherently off policy.
Wait, so meaning you're forcing the model to mimic trajectories generated by an expert under a fixed offline data distribution?
Exactly. And because you're forcing it to mimic offline data, the moment the model makes a slight error at inference time, it just drifts into an unseen state space.
It doesn't know how to recover because it never learned to navigate its own mistakes.
Right. Those errors compound, and you get catastrophic forgetting due to distributional shift. Performance on previously learned tasks. Just craters.
The model essentially overwrites its foundational knowledge just to memorize the new data, which, naturally leads us to look at the theoretical counter to this problem on policy reinforcement learning.
Yeah, exactly. When a model learns from trajectories generated by its own current policy, it actually learns to navigate its own state space.
So catastrophic forgetting is mitigated.
Massively mitigated, because the model is updating based on actions it actually took. But standard RL requires an explicit reward function.
Right.
And if you're trying to teach a model complex real-world tasks, defining a mathematical reward for something abstract like good clinical reasoning is often impossible.
I know a lot of practitioners usually turn to inverse reinforcement learning, or IRL, to solve that. You infer the reward function from the demonstrations first, and then run your RL algorithm.
True, it's mathematically elegant. But IRL is notoriously difficult to scale without imposing heavy, restrictive structural priors.
It just takes too much compute and engineering overhead for massive foundation models.
Exactly. So the MIT researchers introduced SDFT specifically to bypass that trap. They've developed a framework that turns expert demonstrations into an on-policy learning signal.
Without needing a reward function.
Right, and without falling back on off-policy imitation.
Okay, let's unpack this for you. To solve the off-policy problem of SFT, we need a way to generate on-policy updates. Mechanistically, how does SDFT actually achieve this?
It relies entirely on the model's inherent in-context learning capabilities. For any given query, the framework uses the exact same base model in two distinct roles. First, you have the student.
Which is conditioned solely on the user's query, right?
Yes, it generates a response based purely on its internal weights. And because we're sampling from the student's own distribution, any updates we make are strictly on policy.
So the student is just the standard base model trying to answer the prompt from memory. It's essentially taking a closed book test.
That's exactly it. And then you have the teacher. The teacher is the same base model, but its prompt is different. It's conditioned on both the user's query and a specific expert demonstration.
Oh, so it has the answer right there.
Right. Because the teacher has the demonstration right there in its context window. It can leverage its in-context learning to extract the underlying intent of the expert.
Following the analogy, the teacher is taking an open book test, and the training objective here is to sample responses from the closed book student, but then grade them against the open book teacher.
Exactly. Mathematically, you are minimizing the reverse callback libeler, or KL, divergence between the student and the teacher distributions.
You're forcing the student to shift its internal token probabilities to match what it would do if it had the answer key.
Yes. But computing the gradient of that KL divergence for an autoregressive sequence model is, well, incredibly complex.
Because the policy you're updating is both the sampling distribution and inside the logarithm of the objective function.
Right. Differentiating that requires a very delicate balance of bias, variance, and compute efficiency.
You might be wondering how the authors handled the gradient estimator here, because that is where these architectures usually break down in practice.
Yeah, they explored several estimators. They tested a standard token level estimator, which is known to be biased. They also tested a Rao-Blackwellized estimator.
And from a math perspective, the Rao-Blackwellized estimator analytically integrates over the next token distributions, giving an unbiased gradient with much lower variance.
You'd assume that theoretical superiority makes it the default choice. But the empirical results tell a different story.
Wait, really?
Yeah. The researchers found that the full analytic per token estimator actually yielded the most stable optimization and the best downstream performance.
But doesn't that compute the KL analytically at each time step by marginalizing over the entire vocabulary? Doesn't that introduce a sequence-level bias?
It does introduce a sequence-level bias. You are ignoring how the current token choice influences future states. But in practice, the stability you gain heavily outweighs that theoretical cost.
Because the Rao-Blackwellized estimator still suffers from higher variance in long sequences.
Exactly, since it relies on sampling for the future trajectory. The full analytic estimator smooths out the optimization landscape, allowing consistent learning across thousands of steps.
So we're utilizing a vocabulary marginalized gradient for stability. But if we're trusting this proxy to actually improve the policy, we need to understand the underlying objective.
Right, SDFT isn't just a clever prompting trick to force alignment. If you look at the proofs in the paper, this self-distillation objective is fundamentally equivalent to maximizing an implicit reward function.
Under trust region regularized reinforcement learning, if you're listening to this and you work with direct preference optimization or DPO, this is going to feel very familiar.
The connection to DPO and RLHF is direct. Under trust region RL, the optimal next policy is a tilted distribution. It's the previous policy multiplied by the exponentiated reward.
So if you rearrange that equation to solve for the reward, the underlying intrinsic token level reward essentially becomes the difference in log likelihoods.
Specifically, the intrinsic reward at any given time step is the log probability of a token under the demonstration-aware teacher minus the log probability of that same token under the baseline student.
You're looking at how much more likely a token is when the model is allowed to see the demonstration, and using that log probability delta as your implicit reward.
And optimizing the policy with respect to this implicit reward is mathematically identical to taking the gradient of the reverse KL distillation.
It bridges the gap perfectly. You're getting the on-policy robustness of RL, but your reward signal is derived directly from the model's own in-context understanding.
Rather than a separate engineered reward model.
But hold on, I have to challenge the premise here. This entire mathematical proof hinges on what the authors call the in-context assumption.
Right, the idea that the teacher model actually approximates the optimal next policy.
Yeah. How do we know the teacher isn't just verbatim mimicking the demonstration and, drifting completely away from the base policy's trust region?
It's a great point. If the teacher isn't grounded, the student is learning from a hallucination. The authors anticipated that exact skepticism, and they validated it empirically.
They used the 2-alpaca dataset with a Quen 2.57b base model, right?
Yes. They needed to prove two things: optimality and trust region adherence. First, on optimality. Without demonstrations, the base model only solved 42% of the tool use queries.
Okay.
But when conditioned on the demonstration as the teacher, the success rate jumped to 100%.
A 100% success rate is great, but it doesn't prove the model is actually reasoning. It could just be copying the final API call from the context window.
Well, they conducted manual inspections of the intermediate steps to completely rule that out. The teacher's intermediate chain of thought was perfectly valid, semantically grounded, and logically coherent.
So it was actively reasoning through the problem using the demonstration as a guide, not just shallow copying.
Exactly.
Okay, so the teacher produces optimal reasoned behavior. But what about the trust region? How far did the teacher drift?
They measured the KL divergence to the base policy as a proxy for the trust region. For a standard SFT model trained on those same demonstrations, the divergence was 1.26 nets.
Meaning it drifted significantly. which is exactly why SFT causes catastrophic forgetting.
Right. The demonstration condition teacher, however, had a KL divergence of only 0.68 nats.
Oh, wow. That is a massive difference. It means the teacher remained tightly anchored to the base policy while producing that optimal behavior.
It proves the teacher stays within the trust region, providing a highly stable, mathematically sound target for the student.
The theoretical foundation is clearly solid. But let's move into the empirical crucible. Here's where it gets really interesting. Does SDFT actually prevent catastrophic forgetting in practice?
To test this, the author set up a sequential learning experiment. The model was trained sequentially on 3 entirely distinct tasks. First, tool use, then science Q&A, and finally, a medical clinical reasoning task. This is the ultimate stress test for continual learning. If we look at the standard SFT baseline, the failure mode is immediate and severe.
Oh, absolutely. The moment the SFT model shifts from learning tool use to learning science Q&A, its performance on the initial tool use task just plummets.
It exhibits intense oscillatory interference. Learning a new skill aggressively overwrites the parameters associated with the previous skill.
The model is constantly unlearning its past to accommodate its present, but SDFT, on the other hand, enables stable, cumulative learning.
So when the SDFT model acquires the science Q&A skill, its tool use performance remains stable.
Exactly. And when it moves on to acquire the medical reasoning skill, it retains both the science and the tool use capabilities. It's a genuine accumulation of capabilities over time. And crucially, it's not just about retaining the specific skills being trained. We have to consider how these updates impact the general pre-existing capabilities of the foundation model.
Right. The authors ran a suite of general baseline benchmarks, including HelloSwag, MMLU, and Truthful QA.
And standard SFT produced substantial catastrophic forgetting across all of them, right?
Yes. Even DFT, which is an important sampled off-policy distillation method, suffered noticeable degradation.
But SDFT maintained the model's baseline performance across the board.
Because the updates are strictly on policy and anchored by the teacher's trust region, the model achieves a vastly superior Pareto efficiency between new task adaptation and general knowledge retention.
So we've established that the model doesn't forget how to use tools when it learns medicine. But learning a skill or a format is fundamentally different from internalizing raw, novel facts.
Very different.
What happens when the world changes and the model needs entirely new post-training data? To test knowledge injection, the authors introduced a data set of natural disasters from the year 2025.
Which is strictly post-training cutoff for the Quinn model. This tests whether the model can embed novel factual content into its parametric memory.
They compared SDFT against standard SFT on direct question-answer pairs generated from this 2025 corpus.
And on strict accuracy, meaning all factual details are perfectly correct, SFT hit 80%, but SDFT reached 89%.
Which is remarkably close to an Oracle RAG baseline. An Oracle RAG system with perfect retrieval of the source articles scored 91%.
Yeah, SDFT nearly matched a perfect retrieval system using only its internal weights.
Hitting 89% on direct questions is impressive, but the real proof of knowledge integration isn't answering a direct question. An SFT model can just memorize the prompt format.
Exactly, without ever understanding the underlying facts. The true test is out of distribution, or RA performance on indirect questions.
Queries whose answers depend on the injected 2025 knowledge, but the prompt itself doesn't explicitly reference the specific disaster by name. The model has to connect the dots internally.
And this is where SFT completely fell apart. It had memorized the format, but the facts themselves weren't integrated into its latent space.
When asked an indirect question, SFT failed, but SDFT achieved a near-perfect 98% ode accuracy.
That 98% ODANG accuracy proves the mechanism. Because SDFT forces the student to generate its own on-policy trajectories and align its token probabilities with the teacher's reasoning, it actually updates its world model.
This highlights such a massive pain point for practitioners. If SDFT integrates knowledge that deeply, we have to look at how it handles complex reasoning tasks when the training data itself is flawed.
Because right now, training reasoning models on data sets that only contain final answers is an absolute nightmare.
Yeah, it's a profound structural problem with SFT. If you fine-tune a model trained to produce long chains of thought using SFT on concise, answer-only data, the SFT objective actively penalizes the model for thinking.
It forces the model to truncate its internal reasoning to match the short target distribution.
The authors tested this exact failure mode using the OLMO 37B Think model, fine-tuning it on the medical task with answer-only supervision.
With standard SFT, the model's existing chain of thought was aggressively suppressed. The average token length dropped from over 4,600 tokens down to just 3,273 tokens.
And as a direct result of losing that reasoning compute, the task accuracy plummeted from a baseline of 31.2% down to 23.5%.
Fine-tuning the model literally made it worse at the task because it unlearned how to think.
But this is where the SDFT framework provides a brilliant structural rescue. Remember the dual roles. The student is learning from a teacher that is derived from its own base model.
When the teacher is given the answer-only demonstration, it doesn't just output the answer. It utilizes its inherent reasoning capabilities to bridge the gap between the query and the provided answer.
The teacher unrolls its own chain of thought in the context window.
By unrolling that chain of thought, the teacher creates a high-probability target distribution for the intermediate reasoning steps.
So the student is forced to align its internal hidden states to match that reasoning process. The student is still incentivized to think out loud because the teacher thought out loud.
And when they applied SDFT to that exact same answer-only medical data, the token length recovered to 4,180 tokens, and the accuracy surged to 43.7%.
SDFT allowed the model to adapt to the new medical task without suffering a collapse in its fundamental reasoning behavior.
The teacher effectively hallucinated the missing reasoning data and used it to guide the student.
That is incredibly practical for anyone dealing with sparse or suboptimal datasets. But as with any architecture, we have to talk about scaling laws. Does this framework hold up as we increase parameter counts?
You might assume larger models would be harder to distill, but the efficiency actually scales positively with model size.
They ablated the performance across the Kin 2.5 family, testing the 3 billion, 7 billion, and 14 billion parameter models, right?
Yes, the performance gap between SDFT and SFT consistently widened as model size increased. At 3 billion parameters, the model's in-context learning is relatively weak.
So the teacher can't always extract the complex intent, making the distillation signal noisier.
Right, but at 14 billion parameters, the base model's in-context learning is highly sophisticated. A smarter base model drives a much higher quality teacher distribution,
which provides a much stronger, more accurate distillation update for the student. The smarter the foundation, the better it can teach itself.
Exactly.
But that raises a critical implementation question. How exactly are the teacher's parameters instantiated during the training loop? If the teacher is just the frozen base model, it'll provide stable targets, but it won't benefit from the student's learning.
Right, the teacher will become stale. You've identified the core stability challenge of self-distillation.
But if you go to the other extreme and use the exact current parameters of the live student as the teacher for the next step, the training rapidly diverges.
Because small stochastic fluctuations in the token probabilities get amplified through the continuous on-policy feedback loop, causing massive instability.
So they needed a Goldilocks zone. The teacher needs to evolve, but it can't be tied directly to the live student's volatile gradients.
The solution is an exponential moving average, or EMA, of the student parameters. The teacher's weights are slowly updated as a moving average of the student's weights over time.
This tracks the student's progress, allowing the teacher's capabilities to evolve.
But it smooths out the high variance updates, keeping the KL target stable across thousands of training steps.
So synthesizing everything we've covered today, SDFT presents a highly effective, computationally viable method for continual learning.
Unlike RL algorithms that require massive compute overhead for group-based sampling and reward modeling, SDFT requires only a single on-policy rollout per prompt.
It essentially bridges the gap between the simplicity of learning from demonstrations and the robustness of on-policy RL.
For you practitioners listening, you now have a proven framework to update deployed models continuously.
Whether you need to teach a 14 billion parameter model, a new enterprise API, or update a medical model with new clinical guidelines, you can inject that knowledge natively.
You don't have to destroy the foundation model's core intelligence to teach it new tricks, and you do not have to spend weeks engineering complex reward functions.
We finally have a mechanism to cure the amnesiac savant, allowing these models to form new memories while protecting the old ones. But I want to leave you with a final puzzle to mull over.
Oh, Jonas.
We've established that a model can continually learn and refine its behavior simply by using its own in-context reasoning as a teacher. But what happens when we apply SDFT to noisy, suboptimal, or even contradictory demonstrations out in the wild?
Oh, that's fascinating.
Right. If the teacher model is smart enough and the parameter scale high enough, could the policy learn to extract the underlying intent of a human demonstrator, filtering out the noise even when the human makes a mistake?
If the model can self-correct the training data in real time, that completely changes the paradigm of data curation.
That is the next frontier of on-policy distillation. Thanks for joining us on the deep dive.